say we have paraboloid z equals to 2 minus x squared minus y squared. When we have a cone, z squared equals to x squared plus y squared. So paraboloid cone. What we want to do is find the volume. Solid, bounded below by z squared equals to x squared plus y squared, by a cone, above by paraboloid, z equals to 2 minus x squared minus y squared. And we'll assume when z is positive. So we have paraboloid, we have cone, and we will be concerned only when z is positive, so only upper half. Z is positive, so only upper half of that cone, so we don't concern about what is happening below. Okay, so just imagine you have a cone, on top you have paraboloid, so we have a picture which might look something like this. So we have our paraboloid, which is going to make a hat of on top of a cone, and we have a cone, and we will be considering only the top part of a cone. Okay, so we have a hat, and that's what I did cross section. And if you like, make it bigger. Okay, so we're going to be looking at this piece. Okay. Last piece. And if you like, you can draw your z-axis, x-axis, and y-axis. So we'll try. So x, y, z. Right. So because we're concerned about the volume, so volume equals triple integral. I'm going to put 1. Again, if you like, you also can write the volume as a tuple integral, top minus bottom, make no difference. So 1 dv over our solid, let's call it. Okay. And what we want to do is we want to switch to polar. In this case, because we're working with triple integral, it's going to be called cylindrical. So we're switching to cylindrical. Okay. So switching to cylindrical. Okay. Let's work with it. So if you're in cylindrical, you remember x squared plus y squared is r squared. So in cylindrical, if you look at this function, in cylindrical, that is z minus 2r squared. If you look at this function, that is z squared equals to r squared. From here, we're going to get z equals to r. And we assume that's greater or equal than 0. Okay. So we definitely see what will be the limits for z. Z will be changing from bottom, and bottom will come from a cone. An equation of a cone in our case will be r. So z will be changing from r to the top, and on top we're going to have 2 minus r squared. So that's obvious limits for z. r to 2 minus r squared. Where limits for r and theta. So let's figure out limits for r and theta. What we'll notice is we notice what our region is going to be sitting right here. That's the region we're going to be concerned, because that's the biggest part for x and y. That's the like widest for x and widest for y. So we want to project that on xy plane, and then we want to look what is going on here. Okay, because that's the widest part for x and widest part for y. Because what we do, we project the whole solid on xy plane. We want to see the shadow. And actually, when we do that shadow, usually the shadow comes from their intersection parts. So in this case, shadow comes from at the boundary of a shadow when we do it projection on xy plane. Okay. So now to find what is that shadow, we set two functions equals to each other. So we set paraboloid equals to our cone, and our equation for paraboloid is 2 minus r squared. The equation for cone is z equals to r, so we set in 2 minus r squared equals to r. So we set in these two guys equal to each other. So we're going to get 2 minus r squared equals to r, because that's equation, right? Z equals to r. So we're going to get r squared plus r minus 2 equals to 0. We'll try to solve it. So product equals to -2, sum equals to 1. So we're going to get r equal to 0. So from here, we're going to get r equals to -2 and r equals to 1. So from here, we're going to get two answers, r equals to -2 and r equals to 1. And if we carefully look which one we're going to choose, recall our condition that z should be positive. So we're going to choose r equals to 1. R equals to 1, that's we're choosing r equals to 1 because r equals to z, and that is greater or equal than 0. So limits for r is going to be from 0 to 1. So limits for r is going to be from 0 to 1. And because we have a full circle on xy plane, limits for theta is going to be from 0 to 2 pi. Okay. And now we have limits for all the variables here. So final answer, I guess I'll move on to the next page. So final answer is going to be r is changing from 0 to 1. Theta is changing from 0 to 2 pi. Recall that z is changing on the bottom. It was a cone, z equals to r. On top, it was a cone, z equals to 2 minus r squared. Don't forget to put that extra r, because we're switching to polar or we're switching to cylindrical. So that's going to be answer. And when we got to this point, it's not going to be too bad. So that's easy, hopefully easy enough integral for us to calculate. Okay. So it's a lot of drawing and a lot of trying to eyeball what's going on. So initial setup is straightforward. We will want to find the volume. So we set immediately triple integral 1 dv. When we switch into polar, put in extra r. Limits for z is obvious, top to bottom, bottom to top. And on the bottom, we have a cone. Try to rewrite the equation of a cone in terms of polar. On top, we have paraboloid. Try to write it in terms of polar. And then it's a little bit harder to figure out what will be limits for r. For theta, because it's kind of circle, it was straightforward 0 to 2 pi. And r actually needed to do some calculation to figure out what will be r. But it's not too bad. It's not too bad after spending like 20 minutes on looking at it and figuring out what is going on. Okay, anyhow, let me try to do another example. We have a following picture. So we have a cylinder, x squared plus y squared equals to 1. Then we have a sphere, x squared plus y squared plus z squared equals to 1. And we also assume that z equals to 0. Okay, so those are bounds for solid E. Okay, so we want to find its volume. Let me change the problem slightly. I want to put 4 here. Because if I have 1, then the picture will be different. And actually, you have x squared plus y squared glued to that bottom part. I don't want it to be glued. I want to be little. Let's try to find the bounds. So eventually, we want to switch to polar. So we want to switch to polar. So we want to rewrite or polar or cylindrical. So we want to rewrite everything in terms of cylindrical coordinates. So let's try. So x squared plus y squared equals to 1. It's straightforward to write. So x squared, y squared equals to 1. Straightforward. That's r squared equals to 1. So that is r equals to 1. Sphere x squared plus y squared plus z squared equals to 4. X squared plus y squared is r squared plus z squared to 4, so z squared equals to 4 minus r squared, so z is equal to square root of 4 minus r squared, and we're going to put plus because we are told that c is greater or equal to 0 or something like that. Okay, and from here we can immediately see our limits. R is going to be between 0 and 1. Because we're sitting inside of a cylinder, x squared plus y squared equals to 1. So r between 0 and 1. Theta will be between 0 and 2 pi. And z is going to be between bottom and top. On the bottom, we have z equals 0. On top, we have that function, square root of 4 minus r squared. And as soon as we know the limits, we're ready to set up our integral. So triple integral 1. So it's going to be integral 0 to 2 pi. Those are limits for theta. And limits for r is going to be r equals to 0, r equals to 1. Limits for z, z equals to 0, z equals to square root of 4 minus r squared. Those are limits for z. And initially, we had function 1 because we calculated the volume, but now we're going to put extra r because we're switching to cylindrical, switching to polar. So that's how answer is going to look at this case. At least that's how the integral is going to look in this case. So still have to calculate it, but it should not be too difficult of integral to find